All right. Well, good afternoon, everyone, or good morning, I guess. Glad that I could join you today. Skyping in from Washington, D.C. today, where I actually am getting ready to attend a meeting tomorrow afternoon or tomorrow morning for the NASA Industry Forum related to its latest goal for capturing and returning and studying a small asteroid. So what I'll do over the next 30 minutes is describe what we're working on at Planetary Resources, how we have founded the company, and what we are pursuing to enable asteroid mining and the development of space resources through asteroids. And then we'll just have a little bit of Q&A. I don't have anything specifically prepared for asteroid retrieval, but I'll make some comments kind of after you see the context of the company and how that relates to NASA's current plans. So I will switch over to sharing my screen here. And I assume everyone in the room can hear me just fine. I'll keep speaking at the volume I'm speaking at.
Yes, you're fine.
All right, good. So to start with, Planetary Resources' mission and vision actually isn't one that has asteroid mining in it. Our mission and vision is really opening up the economic sphere of influence of humanity into the solar system and creating an economic engine which allows us to do that. And we believe that that economic engine is space resources and everything that really relates to resources. As humans, we have settled every frontier on this planet either in pursuit of resources or by the utilization of resources locally at those sites. And we believe that outer space will be no different. Certainly with the difficulty and the energy required to access outer space, to be able to use resources where they lie out in the solar system will be enabling if we are to ever settle the solar system in the long term. So this is just to paint a brief picture the way I'd like everyone to think of outer space. We have the Earth, Moon, asteroids, Mars, and the Lagrange points, which I hope everyone in the room is familiar with. And these are essentially the crossroads of space. If you could imagine in the early 1800s when Lewis and Clark were setting out to investigate the West and the Louisiana Purchase we had just made, they passed through St. Louis on their way there, and that was really the last real establishment of civilization that they met with. And there they stocked up, were able to send messages and trade rations, and that was kind of their point of departure. And in many ways, the space near Earth, even as low Earth orbit, could be that place. But we need to start thinking of space really as a crossroads, a place that we can get these resources back and forth in the solar system, and the Earth just being a piece of that. So the company was founded by Peter Diamandis and Eric Anderson. Those who are familiar with commercial space know these two individuals. Peter is responsible for not only International Space University and the Students for the Exploration and Development of Space, which I believe there is still an active Penn State chapter for. Peter also founded the X Prize, which the first of which was the Ansari X Prize, which now lives on as Virgin Galactic. Eric Anderson also was a gentleman who was involved in a lot of different things, most notably being chairman of Space Adventures and selling every one of those tickets for the wealthy entrepreneurs to visit outer space as spaceflight participants. And the two of them really had identified resources as being that next economic engine that we're going to open up the solar system. They came to me after I had finished up the Mars Phoenix mission at JPL, and I had spent about 10 years of my career as a system engineer and as flight director of Spirit and Opportunity and service mission manager of the Mars Phoenix lander. And this really seemed like something for me that was very interesting, hard to refuse, and was something that I think the world and technology was ready for. So in turn, I started developing a team around our near-term goal of enabling space resources, and brought with me many friends and colleagues from the Jet Propulsion Laboratory, people experienced in development of space systems and leading of teams doing complex things. Chris Voorhees and Peter Ilsley up there at the top were both instrumental in leading the teams that built Spirit and Opportunity, and both of them each had a hand in Curiosity. But it's not just a mindset of space know-how and doing things that have been done the way they've always been done in aerospace. I wanted to inject some new thought into the company, and for that reason I brought in our principal avionics engineer, Ray Ramadarai. And Ray was one of the developers of the Core i7 line of processors, one of the chief architects of that. And the mindset that he has in the consumer microelectronics industry in bringing innovation, working through very rapid product lifecycle development, and still working in things that are safety critical and remote. There's a lot of space expertise there. So we're supported by really a broad array of advisors, from science to policy to government to law and technology. And all of these individuals have been extremely helpful, and we continue to grow this group of individuals to help us out. But really what enables it is these guys. Our investors are not only important because to get an asteroid mining company started, you need some visionary folks, but the mindset that they bring to the company and how they have gotten to where they are in life and how they would like us to pursue our goal of opening space for business is very visionary. They have a longer time frame, I think, than many investors do. And in space, time frames can stretch out longer than your typical startup. So in particular, the mindset, I think, is embodied by the quote that's there on the bottom left with Ram Shriram. He was one of the original investors in Google, in Larry and Sergey, when they were still working out of their garage in Palo Alto. And when he was doing an interview with the New York Times, the reporter asked him, Ram, why would you invest in an asteroid mining company? What if it fails? And without skipping a beat, Ram said, what if it succeeds? And that's really the mindset that they think that this is worth pursuing. They certainly think that there's money to be made and that the time is right now, and have given us the freedom to really pursue this in a new way. We've also been successful recently in bringing more conservative and more traditional partners to the table with the recent joining and investment by Bechtel Corporation, one of the world's largest engineering services companies. When Rio Tinto needs a mine built, they go to Bechtel Corporation, and their help and perspective is important today and will be very helpful in the future as we work on what may be some of the largest projects ever undertaken in the solar system, and that's something that is not at all new to Bechtel. So with asteroid mining, of course, that could be something that could take quite a while, 10, 20 years or more. How do we start that activity? And that's really been the primary focus of Planetary Resources, to be able to work on something with a timeline that will close in the near future. And our primary focus has been to gather the information that will be necessary in order to determine the best resources in the solar system to develop, as well as how to develop them. And in mining here on Earth, that starts with prospecting and exploration. And in space, it's no different. So our whole near-term mindset is to improve on the great work that's already been done by NASA in the last 50 years of exploration, and to create capability that was once available only to the government, and to put that in the hands of the private sector and develop it much more efficiently, much more rapidly, and with a very specific goal of identifying the resources, where they are, and the technology to extract them. So we chose asteroids not only because that we believe that will help us open up the solar system for business and help us to really establish that outpost that will allow us to expand further away from Earth. But we chose to do it now because the technology really exists. We've had the basic technology for prospecting asteroids all the way back to the Mariner program in the 1960s. And it's been more than a dozen years since we visited the first near-Earth asteroid near Shoemaker at the asteroid Eros, and about a half dozen years since the Japanese visited Itokawa with Hayabusa. But one asteroid a decade isn't fast enough, and the technology to build spacecraft and deploy them in the solar system is certainly something that is accessible within privately operated business today. And then ultimately, we're interested in this because there is a huge business opportunity. I firmly believe that the first trillionaires in our civilization will be created off businesses that are based on businesses in space. And this is because we're not bound by the confines of the Earth or of one country, but an economy that literally scales globally into the solar system. So it's a huge opportunity, and we're really just at the beginning of what is hopefully a very long future for our planet and for our solar system. So I'm going to try this animation over Skype. It may or may not work. We'll see how it goes here. This is an animation of the solar system starting about 15 years ago. In the center, of course, you can see the sun. You can see my pointer. I'm coming over to Jupiter here on the left-hand side. Mars is here in the lower center, and Earth is in the top. And what everyone is probably familiar with is the asteroid belt between Mars and Jupiter. And when I start this animation, there are about 33,000 asteroids known in the solar system. And over time, you can see here in stop action, the solar system really start to fill up as we are discovering asteroids. With each orbit of the Earth around the sun, we discover many tens of thousands of more, and many of them that are relatively close to the Earth. And you can see the pulsing actually is the phases of the moon coming in. And as we arrive in present day, we're actually passing about 600,000 asteroids that are known in the solar system. And yet, this is still only about 1% of what's known in total. So in 15 years of telescopic exploration of the solar system, we have found more than 95% of the known asteroids that have been discovered in history. And it's really just some amazing statistics. The very large asteroids, there are estimated to be more than 1.5 million of them. We have found nearly 1,000 of them that are relatively near to the Earth, and this is probably just about all of them. There might just be a handful more of this size and this proximity yet to discover. But these are the types of which have killed the dinosaurs. If we look at the near-Earth asteroids and the smaller in size, about 100 meters or so, it's been recently revised that there's about 20,000 of them out there, and we've discovered about 20% of these. And all these stats may be impressive, but for me, the singular stat that is most interesting is that of the near-Earth asteroid population, this is about 10,000 asteroids today, about 17% of them are actually more accessible energetically, when you consider the rocket equation, than the surface of the moon is. So to land on the moon, we can find actually that with that same amount of energy, we can get to about 1,700 near-Earth objects. And if we want to consider coming back, and who doesn't want to make the round trip, more than 50% of the 10,000 near-Earth objects are actually more accessible than the surface of the moon. This is something on the order of 10 to the 15th kilograms of material that actually is closer than the closest celestial object in the sky. So it's just really a different way of viewing the solar system and realizing that it's not always about distance. So what are we interested in? What are the resources that are of most value in the solar system? I'll start on the bottom with the platinum group metals. These are platinum, iridium, osmium, palladium, rhodium, and ruthenium. And these are materials that an asteroid and the overall Earth actually have about the same amount of material in percentage of. But in the Earth, there was a process by which all of these heavy elements, specifically the iron, sunk to the core. And these platinum group metals, being siderophile, kind of are attracted to the iron, and they went right along with it. So the Earth's crust is actually relatively depleted of platinum group metals. And you may be familiar with the lanthanides and the rare earth elements. The platinum group metals are actually 1,000 times less plentiful in the Earth's crust than the rare earth elements. And on asteroids, as we have found from meteorites and analyzing them in our laboratory, in many cases have concentrations that are hundreds of times more concentrated than the most productive mines on Earth. So this is a material that is certainly very useful from an element standpoint. It's the best catalyst we have in the periodic table, and all kinds of wonderful properties, if only it were more abundant. In the middle row, we have iron, nickel, and cobalt. These are what you may be familiar with in iron meteorites. And you can think of this as structural metal. We don't often think about making things out of iron here on Earth, or we don't make complex things out of iron. But with something that is so abundant, these are really the materials that we will build large space structures with. In its native form in space, it is has the property of stainless steel and is in extreme abundance in the solar system. There's enough material for 7,000 tons for every human alive today, and that would be enough to build a skyscraper that would cover the entire planet and would be 8,000 stories tall. So plenty of material to do what we want with. But the most interesting set of resources are the volatiles on near-Earth asteroids, in particular the carbonaceous asteroids. So these are the elements hydrogen, carbon, nitrogen, and oxygen, and the compounds that they form, like methane and ammonia. And water, of course, is the essence of life. We couldn't survive very long without it here on Earth. And it enables life that, of course, is sustaining to life. And in space, it takes on a special purpose. In addition to it being an industrial solvent, we don't often think of water being necessary in industry. It exists in space as something that protects us from the space environment. A cubic meter of water has the radiation shielding properties of the entire Earth's atmosphere and the magnetosphere. And a cubic meter of water at present launch value to deep space is $50 million. And in many cases, you need several dozens, if not hundreds, of cubic meters of water. So being able to get that from space is very valuable. And of course, water is hydrogen and oxygen, and breaking it into its constituent elements via electrolysis, you have rocket fuel. And LOX hydrogen is the most efficient chemical combustion rocket fuel and thrust-to-weight ratio that is available today. And to be able to get that in space in near infinite quantities will really enable every one of these other resources in any operation in space in the future that we hope to undertake. So as an example of just abundance of what's out there, if you take a 75-meter water-rich carbonaceous asteroid like a CV3 chondrite and extract out the hydrogen and oxygen, in a 75-meter asteroid you can have the equivalent of all of the volatiles, all of the hydrogen and oxygen that was necessary to launch the entire space shuttle program, all 135 shuttle flights. When you look at the metals and the platinum group metals, taking an asteroid that is about 500 meters in size, of which there are several thousand known already, we just have to find the ones that are platinum rich, you can have the equivalent of all of the platinum group metals that have been mined in history. So certainly a huge abundance of materials. So to talk more back on the volatile story, really to hammer home the point of distance. This is how we often think of the solar system. We have the International Space Station orbiting 400 kilometers above our heads. Our economy in space extends out to the geosynchronous belt, some 38,000 kilometers up, and then out to the moon, asteroids, and Mars, and they all look fairly separated from each other. But if you look at this like an aerospace engineer and consider the rocket equation, it is really all that stuff in space that is relatively close to each other. And it is the Earth that is far away. And as Robert Heinlein said, once you get to low Earth orbit, you're halfway to anywhere in the solar system. So we really need to concentrate on space as an outpost and as a crossroads for everything that we may do, and consider the ways that we can leverage every ounce, every kilogram of material that we ever make that huge leap from the Earth's surface all the way up into low Earth orbit. So I'm going to skip through these charts just for the moment and get on to some of the other materials here. How do we know so much about asteroids and their composition? And it really all started with meteorites. Meteorites have been raining down on our heads for as long as we have had heads and as long as there has been rain. We have now over 50,000 different meteorite samples that have been collected and analyzed in laboratories, and combining that with our astronomical observations, we have painted a rich picture and created excellent theory on the formation of the solar system and the distribution of material in the solar system. So combining this with our recent space missions, we now have some contextual in the field data, and this is a picture of all but one of the asteroids that we have explored closely, which would be Vesta, and at this scale Vesta would be 4 times the size of this chart. But Letitia, and going to the very first asteroid that we saw ever as a point of anything other than a point of light, it's only been 22 years since we saw an asteroid up close and personal, probably the lifetime of most people in the classroom today. And shortly thereafter we saw Ida, which we discovered to have its own moon, Dactyl. And then about a dozen years ago, 433 Eros, which we explored. And if you're having trouble grasping the scale, I always like to bring in a familiar reference for people. This is the Death Star 2, which is about 77 kilometers across, and if you remember Han Solo going through the equatorial trench, that'll give you a good idea of the scale of these things. So I'll call your attention now to this little dot at the point of the cursor. This is 25143 Itokawa. And it is the most recent near-Earth asteroid we have visited, the only one that we have returned samples from. And in fact, the smallest object we have yet visited in the solar system. It's about 200 meters across by 500 meters. Our local Seattle Space Needle is put in there for reference. And the Japanese Hayabusa mission touched down on the surface of this asteroid twice and were able to obtain very high-resolution pictures. Your car could fit in the spot in about here, and this really starts to get to be something where we can consider enough information to how we would value this object and how we might mine it. So as we orbit around Itokawa here, you can really see a very diverse surface of material and information. If we want large rocks, there's some just there resting on the surface. If you need fines, the north and south poles of Itokawa have been processed to produce very fine material. And these are the type of information that we need just for many more objects in the solar system. So to pick one example, this is second on our list of interesting targets, 2011 UW-158. Key things are synodic period, the amount of travel time that it takes, the overall size of this, which is still not well known. But this is just one example of how much material and how much in situ value that material has on one of these objects. You know, anywhere from mere billions of dollars, if you're talking about the amount of iron that exists and the cost of putting that iron in space. And in this case, the water actually has more in situ value than the platinum might, depending on the concentration of what's out there. But as a side effect of asteroid mining and space exploration, we get the benefit of perhaps the most important thing that we can do at all, which is planetary defense. And as we saw on February 15th with the Chelyabinsk bolide, this is something that we are in some peril of being at risk of, and had this particular meteorite hit a little bit more steeply or hit a little bit closer to town, we wouldn't have been talking about 1,100 injuries in Chelyabinsk. We would have been talking about casualties. So we can't prevent hurricanes, floods, tsunamis, tornadoes, earthquakes, hordes of locusts, but we now have the technology for the first time ever to actually prevent this type of global scale natural disaster. And it comes out of the very thing that attracts us to it in the first place, of developing the resources. So from a technology standpoint, and just the last portion of the presentation here, what we're doing to pursue this is give you a mindset of how we're creating our company and how we're pursuing this goal. Is it really starts with creating the most efficient, most capable, agile team that we can. We don't want a space mission with 1,000 employees making it happen. We want the most simple space mission we can execute with a small and efficient team. Inspired by Elon Musk's success with SpaceX, and because of the nature of the risk that we're taking and some of the new approaches that we'd like to implement, we want to vertically integrate and build as much in-house in our facilities in Seattle, Washington as we can, and use that capability to literally mass-produce spacecraft. Mass-produce being, in the spacecraft world, you know, dozens into the hundreds, but going from where we create one of these things to where we're creating many of them is a significant change in mindset. Technology has been moving very rapidly in developing all this, and rather than keeping up with it, we actually have a mind of where this technology will be getting to. So by turning our challenges into information technologies, we can actually get on Moore's Law and create asteroid mining and asteroid prospecting things as information challenges. How can we send back the data, send back the answer to what resource is present in an asteroid instead of all that raw data? And then lastly, thinking about this as a business, this is in effect a real estate and mining business, and the amount of money that we're talking about for prospecting and valuing asteroids is on par with what the mining industry already spends for finding new ore bodies. Being able to explore an asteroid for something less than $100 million is something that the mining industry is actually already used to, with many mines taking up to $1 billion to develop before they end up having a productive mine. And then perhaps the most important point of all, which many people don't realize in establishing an asteroid mining business, is there are opportunities to create value and develop business and earn revenue at every step along the way. So the technologies that we're developing and the solutions we're creating to many of our biggest challenges are useful to industry, to NASA, to the United States defense, as an example, as they would be for asteroid mining. So it's about aligning those opportunities with things that we're already doing internally at the company to help our development plan along the way. So again, in the interest of time, I'm just going to skip through a few things. Our primary focus, as I had said previously, is in prospecting and in remote sensing. And to that end, we've developed a program of exploration, much like the Apollo program, where Apollo didn't start with a command module and a lunar excluder module in the Saturn V. It started with the Ranger program, where we tried to hit the side of the moon. And then we followed that with the lunar orbiter to scout out landing sites, and then the Surveyor program, and then Mercury, Gemini, and Apollo. And with the Arcid series of spacecraft, we're doing much the same. We need a capability at the asteroid to be able to work in a risk-appropriate implementation for swarm exploration, to be able to distribute functionality, to be able to communicate locally in a swarm, and then via laser communications send that data back to the Earth for any one of a number of asteroid targets. And in the near term, we're achieving that through developing our spacecraft bus and demonstrating it in Earth orbit. So this is me in a picture in our clean room with our Arcid 100 spacecraft prototype. And this is a full-sized version of our spacecraft, which you can see by the gold tube is almost all optic. And then a little bit of sensors at the back end of that, and a very small set of avionics and power and communications technology to drive all that. And this is the payload that we need to place at the asteroid through several kilometers per second of delta V, and use optical communications to communicate with, so we can get the smallest size, weight, and power for what we're doing. And this is a program that has been underway for several years now at the company, and we'll be deploying a small constellation of these in Earth orbit, both as a technology demonstrator and then using this capability in Earth orbit to do remote prospecting and remote sensing of asteroids. In particular, while with a small aperture we can't necessarily do better than some of the telescopes on Earth do, but we can look in areas of space that no ground-based telescopes can. We can look interior to the Earth's orbit around the Sun and discover Atira asteroids, for which there are now only 20 known, but certainly the population is much higher than that, and they're every bit as attractive as asteroids that are orbiting outside the Earth's orbit. So we'll use our Arcid 100s to both detect and perform astrometry and refine the orbits of Earth-crossing asteroids. We will, as the chart shows here on the bottom, gather light curves and determine rotation rates for asteroids. This is something that out of the hundreds of thousands of asteroids, there are only a few hundred asteroids that have this information on, and that can help us down select our most interesting targets. And then ultimately be able to take spectra and determine which asteroids may have properties leading them to be carbonaceous or metallic or silicate, and help down select further from there. So to get into, just very briefly, people often ask, how do you plan on mining an asteroid? And to assume that we know exactly how to design that asteroid mining machine today is a bit naive, because of course we don't even understand the ore body with enough detail yet. But I wanted by this chart to really make a point that in space we'll solve these problems with an abundance of three different things. Unlike mines on Earth, we have an abundance of energy, and it costs nothing to get it. We have 1366 watts per square meter. everything that we do in space will likely be solar thermal driven, using the heat of the sun and concentrating that heat to go through thermal processes, raising melting points. We also have an abundance of a 3 Kelvin sky temperature, so we have an industrial quality cold sink that we can use to radiate heat out to and condense things. And then we also have the benefit of an excellent vacuum that we can use for creation of plasmas and perhaps separation of materials. So, well, whether you're separating metals or whether you're separating waters, you can think of, in our first case, in mining water, it could be as simple in theory as distilling seawater, where you raise the asteroid or a local area above the melting point of water and vacuum pressures, which actually isn't even 100 C. And then condense that back out and have pure water. In returning materials to the Earth, thinking now towards the platinum group metals, which are the materials that are valuable enough to consider returning, there already is commercial capability in SpaceX and soon to be with Orbital for returning things via capsule. NASA is working on technologies to be able to take very compact devices and create inflatable technologies. There is a rapid development in space-based or additive manufacturing to be able to create things from materials in situ. But I'd just like to kind of expand your horizons a little bit and think about the problem in an entirely different way. And this could be using additive manufacturing to create a structure that by itself has properties that are much more conducive to coming through the atmosphere. In this case, lowering the density of a material to 100th or maybe even less than that to create a very low ballistic material that would have very different reentry diameters than a traditional aeroshell might. In closing, just a few comments about mining technology, and this is something for me, having worked as an engineer in NASA programs of several $billion and the complexity of landing on Mars. These machines that are being built by companies to pursue resources here on Earth far exceed the complexity and the scope of anything that has been done for exploring space. And it's driven by economic factors. Billions of dollars were spent, of course, because there's dozens of billions of dollars to be made. And here is a capability where you take one of these platforms, put it out in the middle of the ocean, go through a mile of open ocean down to hundreds of atmospheres of pressure, bringing in all of your energy, dealing with the environment and hurricanes and currents, and then going through another 2 miles subsurface to get down to that oil vein. So in many ways, this technology is far more complicated than the environment that we have in space. In space, all of these things are much more simpler, and we only have to learn how to work in a microgravity environment. So much fewer challenges to overcome. But the general point here is that when there is an economic driver and when there's a reason for developing these technologies, we humans and we engineers certainly rise to the challenge and are able to overcome these technological problems. So I don't see this as a technology challenge. This is really an economic and a business challenge to be able to develop this out. So coming again back to the first point of really this economic sphere of influence in the solar system. Again, we need to think of space as a crossroads. And here I'll speak briefly about NASA's intent in the National Space Policy of sending humans to an asteroid and developing deep space exploration capability through humans, and as President Obama said, to create the capability to live and work in space indefinitely. And doing that by becoming masters of the resources that are out there and really understanding the nature of the resources that are out there and how we would develop in them. So if NASA is to proceed on its goal of returning a small asteroid to cislunar space, as was originally identified by the Keck Institute for Space Studies, which I was a participant of, it is of most benefit if they pursue a resource-rich target like a carbonaceous asteroid. And while these are very difficult to find, the ability to find these dark, small objects really creates discovery in everything else of sizes that are larger than that and the ability to rapidly characterize these objects. So that capability and government investment in that capability is good for all the reasons that I have outlined in my talk already today. For planetary defense reasons, for defining resources, and for understanding the origin of the solar system. And in order to achieve this goal, not only do they have to find the target, but they have to go out and understand the mass of that target and the properties of that target. And there are opportunities for companies like ours and other aerospace companies to provide that initial reconnaissance information of, is this the right asteroid to bring back to the Earth? Does it pose any hazard? Is it the right mass? Is the spin state acceptable for us to be able to control this object? And then once, ultimately, that asteroid is brought back to the Earth-Moon system, we now have a resource. You can think of the rocket companies rolling up their garage and rolling the rocket out into the desert, or mining companies having a test mine that is much closer to where the engineers are working than to where the resource is. And a 7-meter, 500-ton asteroid really, while it may not be a large-scale economic driver, it presents the opportunity to have a resource in its native state very close to the Earth that we can visit much more frequently, that we can have the benefit of human assistance in the early days as automation and robotics technology improves over time, and have something that we can, as an industry, experiment with and collaborate with government on as a resource. So that's the reasons why I think that NASA's asteroid retrieval could be a good thing for industry and for government, and if they are to proceed for it, how I think it can be of benefit. So just a final comment here on our Arcad 100 space telescopes. I'll call attention to the black box in the back here. We actually are repackaging all this technology into a 3U CubeSat and doing our initial launch and demonstration of this technology in the second quarter of next year in 2014. And this is really paving the way for some of our early progress, which will follow on with continued development of this. People in the room might also be familiar with another derivative project that we're doing. We have started a crowdfunding campaign to see if there's sufficient public interest for developing public engagement for our space telescopes when we launched them in 2015. And we are just about successful in this campaign. It's going for another 2 weeks. We're giving the general public ability to both direct the main telescope for taking astronomical observations and conducting their own experiments, for enabling this capability in classrooms and research institutions to have access to an asset that is much more broadly available than larger missions. And then also just to connect the public at large with the excitement and the wonder of our own planet and exploring space by giving people the ability to get that picture of themselves above the planet, we call the space selfie, which has been very popular. So I encourage people to go check this out. If you're interested, pledge your support. We have a stretch goal out there where we are intending on creating our telescope to be able to work in the areas of exoplanet science if we're able to meet one of our stretch goals. And this is really stuff that is enabled by the technology that we're developing and bringing the cost down substantially, and creating a new way of just getting the entire world involved in our exploration. And the last point, we're hiring, always employing interns and co-ops year-round. Go to our website, /careers, for those opportunities. We'll be announcing our summer co-ops early this fall, and are always looking for the most talented and passionate people on the planet to help us with our mission and vision. So with that, I'll stop and take questions, and appreciate everyone's attention.
Chris, thank you very much. That was a great introduction to your company and some of the economic rationale for asteroid mining. We have a few minutes for questions. Any questions here from the audience? Yeah.
What can students do to set themselves apart so they get hired for an internship at your company?
Excellent question. So I often tell people that your degree and your coursework and generally good grades are a plus, but what sets you apart is your participation and engagement with the real world. Those design projects that you work on, capstone projects, internships, and applying what you learn in the classroom to tangible projects, and working in interdisciplinary situations where you're not just with a bunch of engineers of your same type, but you're having to engage with people of different disciplines. And the more that you can do that, both in the classroom and even just from a personal standpoint, whether it's with student organizations or things that you're just doing in your apartment, do as much of that as you possibly can. And it doesn't even have to be space related. It's just really being able to master technology and the design process and creating something from nothing that we really look for in people that we bring into the company.
Other questions? Charlie?
Yeah, Chris, that was a great plug for our course that we're teaching today for students if they want to go work for your company. I think what you're doing is fantastic. I wonder how much of what you're doing is collaborative or in some way synergistic with what my good friend Ed Liu is trying to do, looking at potential asteroids that could impact the Earth and cause problems.
Yeah, well, Ed and the B612 Foundation are good friends of ours, and they're working on an even larger problem with their goal of launching an infrared survey telescope in a Venus trailing orbit. They need to find every asteroid out there that may ever pose a problem to us, and that's something that I want to help them succeed in that, because if they're successful in doing that, of course, our ability to find targets is much easier. We're working collaboratively on a number of projects where we want to create better capability for moving object pipelines and being able to find those points of light in the sky more efficiently and more autonomously. Part of the big challenge for Sentinel's mission and for our own mission is the sheer quantity of information and data that is created, and being able to transmit all those raw frames across the solar system for analysis on Earth. We're looking towards crowdsourcing and algorithm competitions to where we can improve the state of the art of these moving object pipelines. It's things that are very simple for any trained 8th grader to be able to recognize an image, but it's very difficult to teach a computer to do the same thing. And if we can automate this technology, we can really empower the spacecraft to be making that first order cut, and we can send the results back to the Earth for confirmation by the smarter humans. So this is all part of our strategy of making as much as we can into an information technology so that we can make best use of the assets that we've got out there.
Great, thanks. We have more questions.
Great.
In the back?
Hi, thank you for your presentation.
You need to speak up, I think.
Come on up here, Sona.
Around here, that's fine.
I have some technical questions. Towards the end of your presentation, you told that compared to deep sea environment, space has much less risk, but I was wondering if you are considering some space related risks, such as space debris. If your mass-produced spacecraft hits the end of life and they will become space debris, also your method of solar concentration might alter asteroid's trajectory over a long period of time, possibly hazardous to the Earth. So I was wondering if you are considering these possible risks, and also I wonder whether taking this into account will undermine your profitability in your business model.
Taking the risk into account is that your last part?
Yes.
Yeah, so great points on all of those. With regards to orbital debris and space debris, our low Earth orbit missions are low enough that they will naturally decay just due to atmospheric drag before any long duration. So things that are just a few hundred kilometers in height don't have any longevity and will naturally decay as a result. As we are creating spacecraft to go deeper into the solar system, the aspect and the risks posed by orbital debris are very slight. Even the millions of asteroids that exist out in the asteroid belt have never posed a problem for the spacecraft navigating through to Jupiter because any average asteroid actually is more than 1 million kilometers away from the nearest asteroid that's out there. So space is a very, very big place. with regards to modifying the orbit of asteroids, this is something where the great benefit in space is that everything in space happens very slowly, and you can, of course, monitor it very carefully. Most of these asteroids that are out there are not on a collision course with Earth, and in fact exist at energy potentials that wouldn't have them ever coming close to the Earth. And any activities that we would do at the asteroid wouldn't substantially change that. The solar pressure that these asteroids experience over their lifetimes and the radiative effects of things like the Yarkovsky effects actually limit the lifetime of asteroids to only a few tens of millions of years of the natural effects that are already out there. So here's a case where we can actually use our influence and our ability at the asteroid to more properly maintain their orbits, perhaps, if they're going to become a threat. And as we have seen in regulation and monitoring of activities on Earth, consider port operations of a seaport, where you have multi-billion-dollar assets with huge amounts of mass coming in and out of population centers. And in the United States, they do that under the watchful eye of the U.S. Coast Guard and the port authorities. And you never, of course, hear of accidents happening at ports because they're all very closely monitored. And in space, I would expect the regulations to develop in such a way that we have that same type of oversight in the activities that we're doing to ensure the safe and regulated operations of activities in space. So fortunately, we have a lot of parallels on how we have done things which may pose some risk here on Earth, and we can extend a lot of that mindset into activities in space. It quite literally is just another place, and is something that we're able to operate in safely and appropriately, and in the appropriate amount of risk. So I think I have time for about one more question.
One more question in the back there. I saw.
My question, there's a lot of teachers in the classroom. I'm a teacher myself. I use Zooniverse. I don't know if you're familiar with that.
Very familiar with Zooniverse.
Crowdsourcing. Are you planning on working with companies that are doing this already? Or are you going to be doing something of your own? And I guess how do we as teachers help you to accomplish your goals in the near and then long term?
Oh, well, in the near term, what we have launched on Kickstarter is a way of getting this capability and the experience and the connection with space on a much more personal level. As a student, I was the benefit of many mentors and workshops and environments which gave me access to learning how one works and supports the development of space capability. And one of the most enjoyable things in my entire career was to be part of the team operating the rovers and landers on Mars, and to work with a group of people to pose a question, to come up with an operational plan, then to transmit those plans out into the universe, and in a short amount of time have the results of those come back to you, is now something that when our Kickstarter funds, we'll be able to give to every classroom of 10th graders in the world. So I'm very excited to work with educators both in the U.S. and internationally to create this engaging experience, whether it is in a university environment, in a public environment, at a science center, or in a classroom environment, and create a curriculum that doesn't just educate you about space itself and the possibilities and the developments in space, but really how science, technology, engineering, and math enable us to do things like this, how it's different than what you see on the evening sci-fi shows and what shows up in the movies. This is the work of scientists and engineers in multidisciplinary environments, asking questions and developing answers to those questions. And I look forward to creating a community around this, to where it's not just the government anymore, but it is really citizen science and citizen explorers the world around enabling this stuff. So I look forward to working with you in some capacity in that regard.
Well, Chris, thank you very much. I appreciate your willingness to come and give us this briefing. There's a lot of excellent information in the presentation that you gave. We're going to be tackling this problem for the week here, looking at all the different elements that need to come, and then look at engaging students on tackling some of these problems. So Stay tuned. Hopefully, maybe there's some things that will come up that you guys will find useful and start putting them into your road mapping for how to do this. So,
all right, excellent.
Thank you very much.
Yeah, have a great day, guys.